When we talk about life in the universe, we almost always imagine it built the same way as life on Earth. Carbon-based molecules, DNA, proteins, and water. But what if life didn't have to look anything like us? What if something else could take carbon's place? Carbon is the backbone of biological molecules on Earth, due to it satisfying the biochemical requirements of life. An alternate element for life must satisfy these requirements, which include adequate chemical diversity, fine balance between reactivity and stability, and the viability to function within a solvent. Silicon, the second most abundant element found in Earth's crust, is frequently explored as an alternative to carbon. In the following sections, we will explore whether silicon fits these criteria. Silicon, like carbon, is tetravalent. However, silicon can increase its coordination number up to 6, expanding its octet. Furthermore, the electronegativity of silicon is lower than that of carbon, meaning bonds with silicon will be more polarized and flipped dipoles with hydrogen. Furthermore, silicon's larger covalent radius means that bond strengths differ with its carbon equivalents. Effectively, carbon and silicon are drastically different elements. Chemical diversity arises from the combination of scaffolding atoms for structural diversity, straight chains, aromatic rings, and heteroatoms to provide functional diversity, alcohols, amines. To explore structural diversity of silicon, scientists computationally substituted silicon into carbon skeletons across different solvents. Results were that the structural diversity had no change in water, due to the frequent nucleophilic attack destroying silicon centers. For sulfuric acid, there were some added diversity due to there being electrophiles instead of nucleophiles, which affects silicon chemistry. Aprotic solvents, however, had the largest increase in diversity as it lacked both electrophiles and nucleophiles, making silicon chemistry extremely stable. Functionally, most carbon analogs like alkanes have their silicon equivalents. However, silicon's inability to form stable pi bonds limits functionality, thus no double and triple bond chemistry. However, silicon has unique silicon compounds like siloxane and silicon oxygen cages, counteracting the lack of pi bonds. Silicon has also been found to be able to form alpha-sila amino acids, showing its potential as the center of peptides. Based purely on theoretical diversity of silicon, silicon satisfies the diversity required for life. The difficulty lies in the compatibility of this diversity in its environment. Therefore, we will explore silicon chemistry in different solvents. In water, pure silicon chemistry is impossible, as silicon centers are instantaneously hydrolyzed due to nucleophilic attack by OH-. The only plausible outcome is silicon being used as a heteroatom, as silicon-carbon bonds are more stable. However, in oxygen-rich environments, silicon is locked as silica, making it thermodynamically unfavorable to reform the stable silicon-oxygen bonds to silicon-carbon bonds. Interestingly, cranberries contain boron-carbon bonds despite energetic limits, suggesting it overcame the energetic barrier of boron-oxygen bonds. We can infer that if functional benefit outweighs the energetic cost, natural selection might be able to overcome the energetic barrier. Thus, silicon as a scaffolding atom is impossible in water, however its role as a heteroatom is plausible. In concentrated sulfuric acid, silicon chemistry is more stable due to the replacement of nucleophilic attack with electrophilic attacks by H+, which affects silicon compounds much less. As a result, silicon-silicon and silicon-hydrogen bonds are stable, allowing stable silicon skeletons to form. Additionally, due to the stronger polarization of silicon bonds, the hydrogen bonds formed are stronger, combating the chaotropic effects of sulfuric acid. Crucially, carbon chemistry is unstable in sulfuric acid, giving silicon a selective advantage. The fact that Venus cloud layers are made from droplets of sulfuric acid illustrates that such environments exist. Hence, silicon life in sulfuric acid is a viable possibility. Aprotic solvents like liquid methane or nitrogen initially appear promising, as it lacks the nucleophiles and electrophiles, allowing diverse silicon chemistry by offering stability. However, solubility collapses at cryogenic temperature, making such environments impossible for silicon life. Therefore, silicon life in aprotic solvents are impossible. In conclusion, many past assessments dismissed silicon biochemistry due to narrow evaluations with solvents. However, once we consider alternative environments, the possibility of silicon's ability to at least contribute to life becomes apparent. Thus, whilst a fully silicon-based biochemistry is unlikely, silicon could expand biochemical functionality as a heteroatom in the right environments. Thank you for watching. Like and subscribe if you want to see more videos like this.